Hey folks, so let's talk about ANOVA, analysis of variation from section 7.5 in the textbook. And hopefully you've already watched the textbook video that I posted. Well, this video of mine is going to pretty much elaborate on that, clarify some of the issues, and well, also I make these videos just so you have some notes that you can reference as well. So this is the last of our long lists of tests. You probably never thought we were going to finish this list, but yeah, we've done all of these except for ANOVA, and today we finished the list. So ANOVA stands for Analysis of Variation, and it's a single test that allows us to analyze means from 3 or more populations. So remember when we had a single population, we did the 1 sample t-test. When we wanted to compare means from 2 populations, we did the 2 sample t-tests. If we have 3 or more populations, well, it becomes quite cumbersome to do a bunch of 2 sample t-tests on like every different possible pairing between the populations. So thankfully, we have ANOVA. It's kind of analogous to chi-squared for proportions. And so, similarly to chi-squared, it's just a single test that it will tell us whether all the means are equal. That's going to be our null hypothesis. The problem is that if the test fails, ANOVA does not tell us which mean is the one that differs, nor does it tell us how many means may differ. So to summarize, and I'll explain a lot of this in a few minutes, we do ANOVA when we're studying means mu1 through mu k, where k is the number of groups, okay? And our hypothesis format will be as follows. The null hypothesis is that all k of the means are equal. The alternate hypothesis is basically just that the null hypothesis is false. In other words, at least one of those means is different. So we have 3 assumptions. The first one is that we have independence both within each group and between groups. This is familiar. We basically had the same assumption back when we did chi-squared, or a pretty similar assumption. The second assumption is that the data is nearly normal in each group. The third assumption is totally new, and it says that the spreads or the variances are roughly equal in each of the groups. So I'll explain more about these assumptions in a second. Our test statistic is the ratio of the so-called mean square of the groups divided by the mean square of the errors, and it lives on a new distribution called an F distribution with degrees of freedom k-1 and n-k, and I'll explain more about that in a second. But finally, we can get our p-value by shading to the right of the test statistic underneath the corresponding F distribution. So let me now explain a bit more about everything that appeared in this summary, starting with the assumptions. So I already mentioned the first assumption is kind of familiar. The second 2 can roughly be checked by looking at box plots. And the third assumption is the one that's totally new. When it's violated, by the way, that's sometimes called heteroskedasticity. And when it's true, it's sometimes called homoskedasticity. So homoskedasticity means that the variance stays the same. When all 3 assumptions are satisfied, that ensures that our test statistic approximately follows an F distribution. And I'll talk more about that in a second. So The test statistic, this thing is kind of brutal. Actually doing the calculations is pretty involved. So to even explain those formulas, I have to introduce the meaning of a whole bunch of different terms. So suppose that we have n total data points, and from that total number of data points, we can find the mean, x bar, of all the data points, but we also split them into k different groups. Suppose each group is of size n sub I, and in each group, we can find the mean in each group, x bar sub I. We can also find the standard deviation of each group. Well then, the top of our test statistic, MSG, not the delicious flavoring that appears in like miso soup. No, MSG is the mean square of groups. And what you do is you add up all the squares of the differences between the group means and the total mean. And you weight them by the number in each group. And then the mean in mean square of the groups comes from dividing by the number of degrees of freedom in the groups. Remember, K is the number of groups. K minus 1 is the number of degrees of freedom in the groups. Okay. So now, if the null hypothesis is true, then all the group means are going to approximately be equal, and all these squares will be very small. And as a result, MSG will be pretty small. And as a result, our test statistic will be pretty small. But when the test statistic is large, that means we are likely to fail. That means we're likely to reject the null hypothesis. The denominator of our test statistic is the mean square error. And here's a formula for the mean square error. You add up the sum of the variances of each of the groups. Multiply it by, n sub I minus 1, which actually cancels the denominator in the variance term, by the way. So it's basically adding up a whole bunch of squares of like the individual values in each group from the center of each group. And then the mean part means dividing by the number of degrees of freedom in all the squares. So this n minus k right here is what we would call the degrees of freedom of the errors. Okay. So yeah, we take the ratio, that gives us our test statistic. Doing the actual computation of this is brutal to do by hand. And probably you never will do a full computation of such a test statistic by hand. You'll usually do it by a computer, and as usual, we'll also use computer to get the p-value. So let's talk about this new distribution, the F distribution. F stands for Fisher. You may have noticed it's doubly indexed by both n and m. It's actually a ratio of two scaled chi-squared distributions, by the way. And in this picture, you can see a few of them, like there in green. We've got F sub 530, for example. They all are supported on 0 to infinity. And once we find our test statistic F, let's say that the test statistic is right here, our p-value is then found by shading to the right. That's what I was indicating in the summary when I wrote this right here. You'll notice, by the way, that the 2 degrees of freedom are the 2 subscripts in the test statistic. So this is equal to F sub, what is it? df sub G comma, df sub e. Oh, as you can see right there. Forgot I had that there. Yeah, so fully justifying this is beyond the scope of this class. So let's do an example. How about with GPA and birth month? So I'm really trying to milk our class survey data for everything it's got. Let's figure out if people born in different months have the same GPA, right? Does which month you were born in matter for the distribution of GPAs? Maybe people born in February are way smarter than everyone else. Okay, maybe I'm biased because I was born in February, but maybe not. So the appropriate null hypothesis would be that the GPA for each month is the same. That is, if mu sub x is the average GPA of students born in month X, our null hypothesis is that mu sub January equals mu sub January, excuse me, mu sub January equals mu sub February equals ... equals mu sub December, against the alternate hypothesis being that there's at least one month with a different GPA than the others. So now let's check the assumptions. The first assumption that we need to check is independence, both within and between groups. So this one, it's kind of hard to say. For one, the students in our class might not necessarily represent all students when it comes to GPA, right? Like if you're an upper division data science major or if you're a data science major in an upper division statistics class at UCSD, you may very well have a GPA that is higher than a representative sample would yield. So that's one problem. And maybe there's some relation between students in our class and their GPAs and their birth month. It's kind of hard for me to think of what that could possibly be. If you have an idea, let me know. But for now, I'll just say that it's hard to say. So I've noted these potential violations here of the independence condition. Next, let's talk about the second assumption, which had to do with normality. And in order to analyze it, I drew a box plot for the GPAs of students born in the different months. I even showed you the code, so you can figure out how to do the box plot yourself. Although if you want to colorize it, you know, some nifty colors, I'll leave you to figure out how to do that. So you can roughly assess the normality of your data by looking at the box plot. Well, for sure, our data in this case is not going to be normally distributed because GPAs have support between 0 and 4. So already we know that they're not going to be completely normally distributed. There's a question as to whether they are even approximately normally distributed. So one of the ways that you can tell whether data is approximately normally distributed from a box plot is whether it appears to be skewed. Now you can spot some pretty skewed months here, right? So everything is kind of clustered up against the maximum value of 4. And then you can also see months, say like February, January, July, December, heck, August. All those appear to have some skew in them. So those are all potential violations of normality. And with regards to the third assumption of homoskedasticity, so we would like each of these boxes to have about the same variance. In other words, to be of about the same width approximately. And once again, we can see that this is probably not satisfied here. For example, December has a couple of very strong outliers, which suggests that the variance in December is potentially relatively large. Similarly, February has a bunch of outliers suggesting that the variance in February is potentially pretty large. So the variance in these 2 months, for example, appears to potentially be a lot larger than, say, these ones, which all look pretty reasonable and close together. So noting all these potential, or I should say, noting these violations, we proceed with the test. And I'm going to do it in R. So we can take a summary of the analysis of variance and then plug in the data. And this is what the output looks like. So you will notice the number of degrees of freedom for the groups is 12 minus 1. The number of degrees of freedom for the residuals, that was n minus k, which was 236 minus 12. R calculated the sum of squares for me, and I can then divide by the corresponding degrees of freedom to get the mean squares. So like this number right here is going to equal 3.34 divided by 11. And this number right here is going to equal 41.52 divided by 224. I can then calculate the F value, the test statistic, by taking the ratio of the mean square of the groups to the mean square of the residuals. So, right, the F statistic, it was MSG over MSE. Here's MSG, here's MSE. Taking their ratio, that's about 0.3034 over about 0.1853. It's about 1.637. So that's my F statistic. Finally, so if I look at an F distribution with degrees of freedom 11 and 224, and I find my test statistic, which is 1.637, and I shade to the right, I get my p-value. And R tells me that it is about 0.0897. So since this does not fall below the 5% level, we fail to reject, and we cannot definitively state that GPAs differ by month. So we cannot reject the null hypothesis. It's possible that maybe GPAs are the same for students of every month, and that all the differences that we observed are just by random chance. We do not have strong evidence to reject, at least not at the 5% level of significance. Okay, so that's it, folks. Thanks for watching. Okay, so first question, why don't you hit the yes or no button? Yes or no? Is this true? Hit the yes or no button. Cool. Okay. Yeah, because it's always helpful to draw a picture, by the way. Probably a good idea to get in the habit of that. If this is n01, that means it's centered at 0. And if this is z sub alpha right there, then that means that this area right here is the area that's alpha. But that's the same as saying that the area to the left is 1 minus alpha. So yeah, you could just as well say z alpha is q norm of 1 minus alpha. Okay, next question, yes or no to this one? Yes or no? Okay. Cool. Okay. I think I saw mostly yeses there. And in fact, you could just use the previous answer to justify this one. Like if you just replace alpha by 1 minus alpha in the answer we just did, that's one way you could answer this question. There's a few different ways you could justify that. Okay. Then moving on, what are we on? This one. Yes or no, folks? Everyone hit the yes or no button on this question. Oh, good. Okay, yeah, everyone's getting this one. Why is this one true?
For the right-hand side of the p norm negative x, the lower tail will be automatically false, and we would be getting the area to the left of x, so it'd be the same thing as getting it for the negative x.
Mm-hmm. Because it's yeah, because the distribution is symmetric. Yeah, okay. Symmetry. Cool. Okay. Next question then. Yes or no to this one, folks? Okay, I'm seeing a mixture of responses, maybe. That's about even on this one, at least assuming all the yeses were yeses to this question and not leftover yeses from the last one. So this one's a no. And why? What should it say? Yeah. So there's more than one way I could write a correct statement, but how about for beta? What should beta equal?
P norm of like -2.
Okay, yes, sure. P norm of -2. That would be one way of writing it. Exactly, yeah. There's like multiple ways you could write it. P norm of -2 would work. Or how about this? P norm of 2 with lower equal to false. In fact, you could even write it as 1 minus p norm of 2. Yeah, so like 3 different equivalent ways you could write it. At least the first one works by symmetry, but the other 2 work by definition of the total probability being 1. So yeah, all 3 of those are fine. Okay. Next question, yes or no to this one, folks? So I saw some no's on this one. What's, for those of you that said no, why? Why no? It's not an if and only if. Well, let's see, maybe this is just a question about P norm and Q norm. Maybe I should draw a picture then for this one.
Yeah, I'm drawing a picture. I think it's helping.
All right, so let's say, I don't know, how about A is right, or no, B is the quantile, sorry. So B should be the number that it lies on the x-axis. So if that's B, then this area will be P norm of B. So that'll be A. So that's the picture here. Well, is B equal to the quantile, the eighth quantile? Yeah, it's the X value that has area A to the left. And similarly, going the other direction. So yeah, this is a true statement. Yeah. So in other words, what would we say P norm and Q norm are?
Inverses?
Yeah, they're inverses. Norm and Q norm are inverses. And a term we haven't officially used very much in this class is that P norm is also the CDF function. It's the cumulative density function of the N01 distribution. So Q norm is the inverse of the cumulative density, which exists since cumulative densities are monotone increasing. Okay, so now we get to some harder questions. Questions 1, 2, 3, and 4. The first one's not so bad. So how about, let's see if anyone can get this one. Why don't you try private messaging me question 1? And if I get a couple answers, I'll show you how to do it. Oh, and you can also Yeah, I want you to write your answer exactly for this one, but you can use Q norm or Z sub alpha notation. So maybe I should just say you can also write like Z sub 0.1, say. Oh, cool. All right. Yeah, I'm getting some right answers there. Yeah. So X is apparently, let's see, mu plus the Z star times sigma. And in particular, if we want it to be in the 90th percentile, then the Z star value, the critical Z value is Z sub 0.1. Okay. If someone has a question, just let me know. And if no one has a question, then we can try question 2. So go ahead and private message me this one. These are all meant to be done by hand, by the way. Don't use R. Okay, so let me write this one. Like, how about if X has a normal distribution with mean 4 and standard deviation 7, then P norm of 1, 4, 7 is probability that X is less than or equal to 1. But that's the probability that X minus 4 over 7 is less than or equal to 1 minus 4 over 7, which is the probability that a standard z-score is less than negative 3. Cool. Okay. Let's move on to question 3. These last two are the hardest. So let's see if anyone can get question 3. You'll probably want to draw a picture. Okay. Got 3 answers and all 3 of them were correct. So let me do it now. So let's say the null distribution is this one. Just centered at 5. And the true distribution is this one. So centered at 7. Okay, so let's first find our threshold for rejection. It's a one-sided alternative. So we're looking for data that's 2 or approximately 2 standard deviations above the mean for our threshold, because the 95% level would have a critical z-score of, well, let me just write it. So threshold will be 5 plus our critical z-score times the standard deviation. At the 95% level, this is our critical z-score. And we're going to approximate it by 2. Okay, so our cutoff value is up here at 11. And it was chosen so that this red area here is about 0.05. Our power then will be an area underneath the true distribution, on the same side as the alpha area, though. So the power will be this area. Okay, so let's see, I guess if I standardize the number 11 relative to the true mean and standard deviation, I can find the area under that to the right. Like I could write this without standardizing as what P norm of 11, 7, 3, lower equals false. But if I want to standardize that, let's see, I'll subtract 7 and divide by 3. I guess I don't even need to write 0 and 1. So is that 4/3? So yeah, I could write it as P norm of 4/3 lower equals false. I could also write it as P norm of negative 4/3. Hey, let's say one of our yes or no questions. Something like that. I know. It's kind of like this one right here. So I could write it as negative 4/3, or I could write it as 1 minus P norm of 4/3. So all 3 of those answers are fine. Any questions on this one? Then let's try the last one. This is the hardest. Seeing a couple of right answers. Okay. Let's see. I think I should draw it first. Drawing will look kind of like the last drawing. So let's see. This is centered at 5. This is centered at 7. Okay, so our threshold this time will be 5 plus a critical z-score times our standard deviation, which is now 3 over root n. And again, we're approximating the critical z-score by 2. Sometimes we do 1.96. That's a bit more accurate, but for this problem, we'll just use 2. Okay. So that's some number. I don't know where that is, but now let's standardize that relative to the true distribution. In order to find the power. In fact, how about I let P equal the power? Okay. If P is the power, then check this out. 5 plus 2 times 3 over root n needs to equal 7 plus z sub p times the true distribution, the standard deviation, which is also 3 over root n. Yeah, because the power is the area to the right of whatever the threshold is underneath the true distribution, but z sub p, our notation is the p is the probability to the right of that point, the upper tail. So that's why this is actually appropriate and notationally consistent. So z sub p is, let's see, root n over 3 times 5 plus 6 over root n minus 7. See, this ends up being negative 2 root n over 3 plus 2. And as we've seen already today, you can take a p-norm of that to get p if you take the upper tail. So p is p-norm of whatever that thing is with the upper tail. Or how about let's write it in a more compact fashion. How about as p-norm of the negative? So that would be 2 root n over 3 minus 2, for example. So now we're better able to answer the rest of this question, which said we want to show that the power increases with n. Well, look at this expression. Does this increase with n? Yeah. Look at let's say standard normal distribution. So if this is n0, 1, and here's whatever that point is, 2 root n over 3 minus 2, it gets bigger as n gets bigger. Okay, this number increases as n increases. So the area to the left of this point will increase as n increases. So we see the green area increases as n does. There's a little symbol for increases, arrow going up. In order to get the power to be at least 95, well, we want this p norm to be at least 95. So if let me say it like this. So p greater than or equal to 0.95 means we have to be past 2. Because remember, we're approximating the 95th percentile of the standard normal distribution with just 2. It's pretty close to 2. So we need 2 root n over 3 minus 2 has to be bigger than 2. i.e., let's see, add 2 is 4, then 3 is 12, add 2 is 6. Root n bigger than or equal to 6, i.e., n greater than or equal to 36. Cool. Okay, so that's this one. Any questions?
Does the green area correspond to the power?
Yes. Yeah,
Okay.
exactly. Okay, so let's see. I haven't talked about ANOVA at all during today's class. So maybe we can do a quick little ANOVA question. By the way, I made a point about this on today's announcement, but the mom homework that's on ANOVA is not due till well after the corresponding midterm. So I recommend that you just do that homework early, so that way you can get some practice with that stuff. It's not too bad, though, I think. So this will be kind of a preview of those types of problems. Let's fill in the missing values of this table right here. Like, does anyone spot an entry that we can answer with the information given?
The sum
Oh,
of
the
squares.
sum. Oh, okay, this one right here. So the textbook video made a point that the sum of the squares of the groups plus the sum of the squares of the errors or the residuals, I'll call it errors, is equal to the sum squares of the total. By the way, I haven't used the word residuals very much, but it means errors. Anyway, so some number plus 50 is equal to 60. So that first question mark is 10. So let's put a 10 right there. Okay. What can we answer now? Some what else can we fill out? So good. The mean of the squares is the sum of the squares, or divided, or sorry, let me say that more carefully. The mean square of the groups is the sum of the square of the groups divided by the number of degrees of freedom of the group. So MSG, which kind of delicious. I think of umami in Japanese food every time I think about MSG. So that's the sum of the squares of the groups. Right? Did you know about umami? It's like the 5th flavor. You thought there was just sweet, sour, bitter, and salty. No, there's a 5th flavor, and it's delicious. And it's called umami. Only the Japanese have a word for it, and you can get it in monosodium glutamate, which is like, it's like super salt. Anyway, the mean square of the groups is sum squares of the groups divided by degrees of freedom of the groups. In this case, it's 10/2, which is 5. Similarly, the mean square of the errors or residuals is the sum of the squares of the errors divided by the degrees of freedom of the errors. In this case, that's 50/20. Okay. And what can we get next? Oh, the F value. Good. F value is the ratio. So F is MSG. MSG. So it's 5/2.5. And this one we would need R for. Anyone know what you would punch into R to get it? Here, I'll just tell you. So what this one's going to be, let's see if I can remember. Well, the probability on an F distribution of our F statistic, or F value, which is 2. And then you need to list both degrees of freedom, which are 2 and 20. And we want the upper tail always. So lower equals F. Let me check this real fast. Okay, so get 16 as my p-value. Cool. All right, folks. So that's it for today. Thanks for participating in the quiz, and yeah, see you all Friday.